Okay, so we're going to use ANSYS now to look at a piezoelectric device, and this is a Unimorph. So this is where you have a piezoelectric element attached to some substrate, metal in this case, and we basically apply an electric field. So in this case the piezoelectric will strain and it will shrink in this direction, and because it's attached to a substrate, will get out of plane bending. So it's a way of magnifying the piezoelectric strain. And remember, in ANSYS, the constitutive equation that relates stress, dielectric displacement, strain and field is given by this equation. So really what we need are the materials properties, the stiffness matrix, the piezoelectric matrix of the material, and the permittivity of the material. We're going to look at a frequency dependence as well, so we'll need the density of the substrate and the PZT material as well. And this Unimorph, let's say it's 100 millimeters long. The width is 25 millimeters, and these layers, the piezo and the elastic, are 0.5 millimeter thick. So in total, this thickness is 1 millimeter. And what we're going to do is apply a potential difference of 100 volts across the piezoelectric element to get out of plane deformation. So there's a nice paper here. It has some piezoelectric properties of the material, PZT5H. So this is a sort of soft piezo, soft material, so relatively high piezoelectric activity. So this is the stiffness matrix in the paper, and then this is the ANSYS format. There's always a subtle difference. So in this case here, you can see this is C66 in the paper. What ANSYS wants is C66 in this location, in the C44 location in a way. So we just have to be careful of that. There's not much difference, but it's good to get it right. So we'll input that into ANSYS when we load it up. The Piezo Matrix, this is in the paper again, so this is the charge density per unit strain. So these are the E31, E33, and these are the shear coefficients. Again in ANSYS, those shear coefficients, E15, are just in a slightly different position. So again, you need to be careful. There's no real shear in this device, so it'll probably work. But again, it's good, obviously good to get it correct. I looked up the permittivity of constant strain. Remember, you need that value. You can also get values of permittivity of constant stress. But remember, what ANSYS wants is the constant strain values, because it's in that constitutive equation here that it's using to solve the problem. So again, I've got the data, and the density of PZT is quite dense, 7.5, similar to steel. Because it's got lead, it's lead, zirconate, titanate, so heavy elements. Okay, so let's try and see if we can model this now. So I've loaded up ANSYS. So we have a structural model, and so obviously we're going to have some electric field as well. So we define our preferences, then we define which elements we want. So we need a coupled field element to do the piezoelectric, and that's following that equation, our coupled field constitutive equation that I showed earlier. So we'll use a brick, because it's a 3D model, so element 226 here. So element 226 has a variety of options, structural, thermal, so it tries to do other things as well. So we'll just tell it to look at piezoelectric applications. Okay, solid 226, and then our substrate is aluminium, remember, so that doesn't need to be a piezoelectric element, so that can be just a straight solid element. And again, the piezo is a 20 node brick, so we may as well use solid 186 as well to keep that consistent. Good, so there's my piezoelectric element, and type 2 is my structural element. That's good. So the next stage is to add in our materials properties. So materials models. So material 1 will make the piezoelectric. So it's a structural aspect that we're going to put in first, the stiffness matrix. It's a linear elastic matrix, and it's anisotropic because it's a poled material, so it has a preferred orientation. So these values of D1, D1, 2, etc. This is basically the values for the stiffness matrix. You can see it's in stiffness form. If you have compliance data, you can put it in flexibility form, but in the paper I found I had the stiffness matrix. So let's insert those, make sure we get the right units. So the units you almost define by what you put in, so I'm going to put it all in SI units. So 1.26 e to the 11 pascals. C12, so again I'm just looking at the stiffness matrix in the paper, 7.95 e to the 10 pascals. 8.41 e to the 10 pascals. So C14, C15 and C16 0. C22 1.26 e to the 11. So that's the same as C11 because it's the same in the X and Y direction. And my C23 is 8.41 e to the 10. So that's the same as C13. Again, 0, 0, 0. And then my C33. So I have a slightly different compliance in the stiffness in the 3 direction compared to the 1 and the 2. And that's because it's polarized along the 3 direction. So you have a different stiffness along there. So again, that all makes sense. Always good to think of the values that you're actually putting in, if they make sense as well. So remember, C44 is effectively my C66, 2.35 e to the 10, 0, 0, C55, 2.3 e to the 10, and 2.3 e to the 10. So that's again my C44, which is equal to the C55. Good. So that's my stiffness matrix. Let me just check the units are all okay. That's good. So I've got my stiffness matrix in. So the next one is the piezoelectric matrix. So again, I've got it in my stress matrix, which is charge density per unit strain. But again, if I have a D matrix, which is charge density per unit stress, I could insert that, but I've got E values, so minus 6.5, minus 6.5 for the E13, E33 is 23.3, and then my shear coefficient, C15, 17 coulombs per meter squared. It's good. And then I need the permittivity at constant strain. So relative permittivity, not permeability. And in this case, I've got a permittivity in X, Y, and Z. Remember, it's different in Z because it's polarized along Z. That's why it's active. So that has a slightly lower permittivity at constant strain compared to the X and Y. Good. And then I'll put in a density because I'm going to do a frequency dependence as well. So just double check, 7,500 kilograms per meter cube. So again, I'm keeping everything to SI units just to keep it simple. So that's my piezo. So now I add a second material, which is, remember, my aluminium substrate. So it's a lot more simple, elastic. In this case now it's isotropic, same stiffness in every direction. Remember, I'm in SI units, so it's 70 gigapascals. Poisson's ratio 0.3. and I also need a density. So my density again for aluminium 2,700 kilograms per meter cubed. It's good. Good. Right. So I got my two materials in, and I got my two elements in. So the next stage is to start to create the device. So I'll create a volume by dimensions. So it's 100 millimeters. So 100 e to the minus 3 in the x direction. It's 25 millimeters width, e to the minus 3. And this first volume, I'll make it the piezoelectric. It's 0.5 millimeter thick in the Z direction. And again, I've chosen the Z direction because that's the polarization direction defined by the materials properties that I've input. So that's okay. So I've got my first element volume there, and then I create my substrate. And again, it's going to be the same length, same width, but the main difference is it's just going to be on top. So it's 0.05. That's going to be 0.5 millimeter as well. So it's going from 0.005 to 0.001. Great. So I've got my two volumes now. But obviously, in a way, I've created them, but they're not joined together in any way. So I need to operate on them. In that sense, I need to glue them together. So a Boolean glue volumes, and just pick them all, and I've glued them together. And what the glue does is that it bonds them together, but it keeps them as separate entities because then they're separate materials. If I added them together, it would just create a new volume, which is the addition, and I can't make them separate in terms of materials properties. So that's why I've used the glue function. Okay, so we can now move on to meshing. So I need to now tell ANSYS which of these volumes are the piezoelectric and which are the substrate. So let's just zoom in here, just make it a bit easier. My mouse control is not very good because I'm just using a trackpad. So this top layer here, I'll make that the piezoelectric material. So mesh attributes, picked volumes. So this volume here, which is going from 0, 0, 0 to 0.5 millimeters. So that volume, that's going to be material number 1, because remember that was the piezoelectric, and that was going to be element type number 1, because remember that was the piezoelectric element. So that's okay. And then the other volume, again we'll just do it by pick, that'll be the aluminium. So in that case, that will now be material 2, because that's the material that we assign to the aluminium properties. And for that, we don't need any piezoelectric, we just need to be a structural element, follows Hooke's law. So we make that solid 186. Good. So we're doing all right. So created the shapes, we've glued them together, and now we can mesh. So we can just use the smart tool. So we can just use mapped meshing. Just do smart size mesh. Pick all. Good. Okay, so I've got my meshed elements. Let's just zoom out. Yeah, so I've got my meshed glued volumes that have been assigned the appropriate elements. Right, so the next stage is now to put on some electrodes in order to apply a potential difference across the piezoelectric element. So remember that was going from 0 in the Z direction to 0.5 millimeters in the Z direction. So what I can do now is just select the nodes at the 0 in the Z direction, so in the way that the base nodes, and do that by location in the Z coordinate. So I select all the nodes on the 0 position in the Z axis. Okay, and if I just do plot nodes, you can just see I've just got one array of nodes, and if I look at it side on, in a way it's just a line. So all those are the nodes in the bottom of the piezoelectric, and I use a command here, so it's CP1, so it's couple set 1 in the degree of freedom volt, all the selected nodes. So what that means now is that all the nodes on that location will all have the same voltage. So that's exactly the same as you'd have as if you had an electrode painted on the structure. So if you now select all the nodes, and let's just plot, replot, just to make sure. Yeah, so I've got a couple set at the base of the piezoelectric, and now I need another couple set, another electrode, which is on the other side of the piezoelectric. So I select entities by location. And remember, this is at 0.5 e to the minus 3. So 0.5 e to the minus 3. Plot nodes. So that's on the other side of the piezoelectric. So again, I can use my commands. Coupled set 2 in the degree of freedom volt, all those nodes, and that's my second electrode. So if I select everything, plot, replot, and if I zoom in, you could hopefully then see, so there's the piezoelectric between those two coupled sets, and I've got one electrode on either side of the structure. So now I have my two electrode materials. Ooh. Good. So just out of interest, we can use a couple set list command, CP list. So we should have two coupled sets. So coupled set 1, and what I tend to do, I just note the first node, because that's the master node, so all the others will follow. So in coupled set 1, it's element 1, and we should have a second set. Yeah, that's good, so let's write that down. So in coupled set 2, the master node is 737. So again, I can just select that node if I want to apply a voltage to all of these elements. I think that's good. So now we can just go to solution. So we're going to start with a static analysis. Just going to look at the static displacement, and we want to clamp our piezoelectric, remember. So if we look back at the structure, so it's clamped here at the side, a bit like sort of holding a ruler and deforming it. So we need to clamp the material. So let's just zoom in and look at the right at the origin. So what I can do is apply a load, apply a structural displacement on the nodes. I can use a box. I could pick location, but I can use a box to select all the nodes at that origin, and I just clamp it in X, Y, and Z, and so I fix it to a 0 displacement. So I've got my clamping there. So I've got it clamped at the end, and now I just need to apply my boundary condition, my voltage. So I'm going to apply 100 volts across the structure. So on nodes. So remember, coupled set 1, the master node was 1. So if I just select number 1, So I saw something happen there. There it is, this number 1. So if I put that to earth, 0 volts. So the base will be at 0 volts. And then at 737, which is the master node of the other coupled set, yeah, it's there. I can select that as 100 volts. So I have a potential difference of 100 volts across half a millimeter of piezoelectric. So that should be enough. I don't think I need any other conditions. I've clamped it, I've got an electrical load, I have my elements, so we can look at solving. So it's solved. So this is the moment of truth. So we can look at the solution. So I'm using a remote desktop, so sometimes it's a bit slow. So plot my results. So let's just look at the deformed shape, and it's moved, so that's good. So I've got a displacement, so you can see it's moved downwards out of plane. And so what I can do now is just look at the value of that displacement in the Z direction. So nodal solution, Z component of displacement. And I've got a displacement. Remember, this is then all in meters because I've kept to SI units. So 0.398 e to the minus 3. So 398 microns. So let's just write that down. So my displacement of my device. So you can see this is a relatively small strain, but it would be even smaller if it was just a piezoelectric on its own. So by attaching it to the aluminium substrate, I'm getting some out of plane deformation, and so the longer that structure I made, I would get even more displacement, so I can amplify. So I'm getting 398 microns. Now, is that reasonable? Is that an okay value? Well, for this structure, for this material, I found a nice paper here. So it's always good to do this sort of thing if you're going to do an analysis. Do something similar, and do something similar that you can find some analytical solution. So this is an equation here for the DC deflection, so the static deflection based on the length, the height of the piezo, the voltage, and the D31, which is the sort of contraction in response to an electric field. And A and B are sort of geometrical parameters and stiffness parameters. So we know our piezo stiffness and our aluminium. We know the height, 0.5 millimeter. We know the length, 100 millimeter, 100 volts. And this is the D31 of PZT5H. So we got 398 micrometers. And so my calculated value from the analytical equation is 410. So that's pretty good. That's not too bad. So I'm relatively happy there. Okay, so let's just see if we can do an AC response. So rather than a static response, let's do a harmonic analysis. And rather than a static 100 volts, let's sweep the frequency that we apply to that 100 volts over a frequency range. So let's do a more dynamic analysis. Frequency and subsets. So let's go to 700 hertz, from 0 to 700 hertz, and let's go in 10 hertz subset steps. Just put a little bit of damping in, So this is just a typical damping coefficient that I sometimes use. You can change those, and sometimes I measure them experimentally, because this is a difficult one to get, because it's not just a material here, because you have PZT and aluminium, have a bonded structure of two materials, so it's difficult to know exactly what the damping coefficient. So we're going to go from 0 to 700 Hertz and solve that. It's going to, I guess, take longer because we're doing a series of runs. So just bear with me a minute while it solves. I think I could limit the amount of data that's output by ANSYS and speed it up a bit, and also it's a bit slower because I'm on a remote access, but let's see how long it takes. I'm sure this is exciting viewing if you're watching. And while it's solving, so again, what I've done, this was the DC value. Remember, pretty good agreement, not too bad. Again, because the stiffness in the equation, it's sort of isotropic assumed, but it's clearly not. So I had to make an estimate, an average of the X, Y, and Z stiffnesses in a way. So there's an error here. So reasonably good agreement. And then also in that same paper, there's a nice equation here for the first mode of resonance. Again, knowing values of the dimensions and the stiffness. Again, it's assumed that it's sort of isotropic because there's just one value. And remember, it's got different values in each direction. Still solving. I can never understand if it was running then in the background while I was looking at PowerPoint. Probably was. And this is where I always regret that I've put too many sub-steps in. Never mind. Good. So our solution is done. So what we can do is look at time hist post-processing. So, okay, so let's have a look. So we've got data from 0 to 700 Hertz. Let's just look at it here. It's clamped, remember, on this side. So what we'll do is that we'll look at the Z displacement of a node. Let's look at the node at the end. So when it reaches resonance, then obviously the displacement at the end will be larger if we're going to reach the resonant frequency of the structure. So I've just selected the node at the end, so we should load those in. So it's just loading those. Z component of displacement of node 2768, which is at the end of the cantilever. And if we plot that against frequency, nice. So we have two resonant frequencies. So we have a first one at around 60 Hertz. There's an estimate around 60 Hertz. The first mode, and then we have another mode here. If that's 400, 320, approximately 370 Hertz. So 60 Hertz is the sort of first resonant mode, and if I look at the equation and what we put in, I get about 54 Hertz. Again, I'm reasonably happy with that. Again, because there could be errors in the meshing, etc. But also I've made an assumption here that this material is isotropic and taken an average value there. So that's pretty good. Pretty happy there. And we can also just look at the actual mode of deformation at those frequencies. So if we look at 60 Hertz, just read in there the 60 Hertz data, and then if we plot the deformed shapes, that should be first mode, so that should be fairly simple. Yeah, and so you can see just a first mode where we got sort of half a wavelength along there. And if we then look at the other resonant that we saw, which was at 360 Hertz, so let's just look at that data. And if we plot those results, deformed shape, deformed and undeformed, yeah, that's quite nice. Again, it's what you'd expect as a resonant. Let's just do that, just look, so you can see it's clamped here, and you get a higher resonant mode, and certainly I see those modes on cantilever beams that I've been using for energy harvesting applications. So good, so hopefully you can be able now to use ANSYS to model piezoelectric unimorphs. There's no reason why you then couldn't use this skills to use bimorphs, where you have two piezoelectric layers with opposing polarity to get even more displacement. So I'll finish there.